This hard rock mine in the mining camps of Victor, Colorado was responsible for digging out gold. In addition to gold found in these rocks, there's also a lot of iron. Now, iron is one of those elements that reacts greatly to Earth's magnetic field. Long before humankind knew anything about Earth's magnetic field, stones containing large amounts of iron, called lodestones, were found interacting with each other. These stones and their interactions were first observed in Magnesia, Greece. These stones have since been called magnetite. Magnetite contains a huge amount of iron. It has been observed that if iron is left undisturbed for a long period of time, this iron will align itself with Earth's magnetic field. Well, we've spent a lot of time in doing various demonstrations regarding the comparison between electric charge and magnetic poles. So let's focus our attention down to magnetic poles. Okay, magnetic poles. Well, we have seen that an area of influence around a charged particle was defined as the electric field. That's exactly how we define the magnetic field. The magnetic field is the area of influence around a magnet. And that defines for us the magnetic field. Now, the magnetic field is going to be a topic that we spend the next several lessons talking about. And we symbolize the magnetic field with a capital B. Not quite sure where B came from, but nonetheless, that is the accepted shorthand symbol used for the magnetic field. Well, we also we've seen now the area of influence around a magnet. That's what the previous demonstrations were all about. And so we can now talk about the magnetic field. If this is the North Pole and this is the South Pole, we recognize that North Pole field lines, magnetic field lines, leave the North Pole and enter the South Pole. Now they go in both directions, and what's impossible for me to clearly show is their three-dimensional nature. But just like the electric charge, it is three-dimensional in a sphere. We've got a whole bunch of field lines coming in and around these magnets. So we've got a field that looks like a bunch of hamburger buns. Okay, so here's the top bun and here's the bottom bun. All right, so that's how I remember the shape of the magnetic field. And this is why you can't separate North from South Pole. It leaves the North and enters the South. Now, that was almost an ambiguous statement. It really was quite an ambiguous statement. It's not this is why one enters and one leaves. That's what we observe to happen. So we're going to talk about a little bit more about why you can't separate them in just a moment. But before we do, a couple more drawings I wanted to make for you. Okay, now we also saw a magnet, two magnets with iron filings. Now, this was the North Pole, and this was the North Pole. That was the South, that was the South. We saw these magnetic fields, so this was, wait. We first discussed attraction. So let's make that the South Pole and that the North Pole. Okay? So what we saw was these field lines arched clear up and over to the other end. Now, we couldn't tell from the iron filings which was north and which was south, but what we could tell was that the shape of this field was that of attraction. And we saw the iron filings line up and orient their domains, or orient their atoms along these field lines. Now, what did we see in the middle? We saw in the middle these field lines start to get more and more straight. And then as you got closer to the ends, you saw them start to interact in this way. So we end up seeing this, and probably a better way to consider it is along the sides. If you can envision to explain what happens in the middle, I mean, this is what we observed went on. We saw these field lines go almost straight across from each other. And so you could orient yourself to north and south. Okay, well, when things were, this was for attraction. Okay, attraction. Repulsion, we saw a very different pattern. When we were looking at repulsion, let's just call this the inside as North Pole and the inside edge is the North Pole again. What we saw here was that these field lines avoided each other. Okay? There was this repulsion going on inside. Now, we don't know if this was a north and a north or a south and a south, but what we can see and what we can observe is that the magnets did not want to connect with each other. They were definitely not attracting each other. They were repelling each other. And so you get a picture that looks like this for repulsion. And so we've got a diagram of magnetic field lines. Now, just like electric field lines, we're able to show the direction of the magnetic field. It's going from north to south. Second, we're able to identify the shape of the field, and in this case, we can identify the shape of the field by iron filings. We couldn't do that. We didn't have a demonstration to show that for the electric field. And the third thing that you can see is that wherever these lines are very, very close, the magnetic field is very strong. And as you got further and further away, these magnetic field lines got further separated from each other. That's where the field was significantly weaker. So everything has been in comparison to electric charges, right down to the field lines. Well, what does any of this have to do with charge? We've seen lots of similarities go on. But the question is, where does magnetism come from? And we said in the beginning that the principles, the fundamental principles of magnetism were born in electrostatics, in electric charge concepts, but we haven't seen any of that. All we've done is just kind of parallel observations. Well, the connection actually came accidentally. It was accidentally discovered in right around 1819, 1820 by Hans Christian Ørsted, who had a demonstration similar to this one set up, where he had a wire that was connected to a power supply and thus creating a circuit, but he also had a compass sitting nearby. Now, what he noticed was that when a compass was put next to a wire that wasn't carrying any current, nothing happened. There was nothing going on. But watch the needle when the circuit is made through pressing the switch here. Watch the compass needle. Okay? What he showed and accidentally discovered was that a current-carrying wire could deflect a compass needle. Well, if a current-carrying wire deflects a compass needle, and a compass needle only reacts to a magnetic field, then there's got to be some connection between charge in the wire and magnetic field. So that is the accidental discovery that got the ball rolling between asking the question of how is the principles of electricity connected to the principles of magnetism.